data structures and algorithms. So right, today we're going to be talking about time complexity. And what is time complexity? So time complexity tells us how fast a program runs as the input size grows. So let's say, when I say input size, let's look at this very simple data structure. We have an array of numbers, right? 1, 2, 3, 4, 5. And we want to calculate the total of that number. So in real life, what would I do if I want to count every element that's here? I'll say, okay, I have 1, I have 2, I have 3, I have 4, I have 5. Now, how can I do this in code? So I can get a total which is equal to 0, and I can say for each time that I see an element here, I want to add it to the total so I can get the correct answer. So now what I can say is total plus 1, total will be 1, right? 1, total is now 1. 1 plus 2, that is 3. 3 plus 3, that is, 1 plus 2, that is 3. 3 plus 3, that is 6. 6 plus 4, that is 10. 10 plus 5, that is 15. So that's what this for loop is doing. So for every number inside nums, we're going to be adding to total. In a situation like that, when we're talking about time complexity, our input size here is 5. The number of times that I had to count 1, come back 2, come back 3, come back 4, come back 5, that was 5 times. So because I had to come back 5 times, the steps is an O of n solution, right? It's an O of n. And let's look at it again. So if it was only one element in this entire array, it would still be an O of n, but the number of steps I'll go is 1 time. If it was 5 elements, number of steps will go 5 times. So if you look at this graph that I have over here, right, the green is the O of n. You see how as the input increases, the time it takes for this to run increases too. And why is this important? Let's say that you're tasked with building a dashboard at work or something that is more complex with a lot of data. The way you retrieve the data and the way you manipulate the data using code matters, because that might affect how the data is retrieved, how fast users can see the data, and how fast they can also research things too with data. Now, let's continue. Let's look at a nested loop now. So I want to print everything here in I and j. So I'm going to loop through I the first time. Then I'm going to loop through j the second time. So now I have to loop through it 2 times for me to actually see this. Let's see if this can run. So can you see how many times I have to loop through this? So I have to loop through I first. Then I have to loop through j. So for each I loop through I. So I have 1, 1. Then I'm looping through j. So I have 1, 2. Then I have 1, 3. Then I'm going again. I have 2. So now I'm in the second iteration for I. I have 2, 1, 2, 2, 2, 3. So we had to go through this several times, right? And because of that, it's like I'm going through it twice. So I'm looping through it 2 times. So now, guess what type of time complexity this will be? This will be an O of n square, because I'm going through it twice to get here. So now, 1, 2, let's see how many iterations they had. 1, 2, 3, 4, 5, 6, 7, 8, 9. And these were 3. It ran 9 times. So we see that we basically it basically duplicated the number of times. So it squared it basically. So now this is an O of n square. And an O of n square is actually worse than an O of n. So as you can see, O of n is this green line here. You can see that it gradually increases as the number of elements increases. But when we look at O of n square, it's shooting to the sky. So we see that it's more. And because of that, a lot of people don't like using O of n time complexity, because it increases so much based on the input size that we're getting in. So the number of steps increases. So I hope you're understanding this. So let's look at a binary search algorithm now, and let's see let's see the time complexity of this. So when we talk about binary search, we're finding a specific target in a sorted array, right? Let's say that I want to find 5, right? Let's say I have an array and I want to find 5. So let's say I have an array of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And I want to find 5. And my target is 5. So my target is 5. Now, what are things that I can do? In a binary search approach, I would just keep on dividing this in half until I find the target. So I would have a left pointer, I'm going to have a left which is at 0, and I'm going to have a right which is going to be at the end. And what I'm going to say is I'm going to find the middle of this. And if the middle is equal to the target, then I found my solution. If not, I'm going to increment left. So I'm going to be making it smaller and smaller until I find my solution. Okay. Now, in a situation like this, right, if we're looking at the number of steps that we're going through, this is an O of log n, because for each 2 steps, right, for each 2 inputs, right, for each inputs, right, for each 2 inputs, I'm moving 1 time. So this is actually better in terms of like space and time, in terms of time. So let's look at our graph. So we see an O of log n is orange. You see how it's not rising, it's actually better. I believe at a point in time it's not rising. Basically, at a point in time it starts to reduce. So basically, the number of elements, the number of values, the number of inputs is higher than the number of steps it takes for me to run through the entire data, which is good, right? So O log n is actually good, and this is contrary to what I thought before of it being bad just because I saw log, right? But it's actually a good thing. So I hope with just this brief presentation, I hope it blessed you, and I hope it helps you to do better at work or in your next interview coming up. Have an amazing day. And data structures and algorithms. So right, today we're going to be talking about time complexity. And what is time complexity? So time complexity tells us how fast a program runs as the input size grows. So let's say, when I say input size, let's look at this very simple data structure. We have an array of numbers, right? 1, 2, 3,